Hello everyone. I will be starting with the session now. Dear authors and invited guests, welcome to Technical Session 15D. My name is Dimahi Patel and this session will be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic LLP, it is my great pleasure to welcome you to the 10th International Congress on Information and Communication Technology, London, United Kingdom. The 10th edition of the conference is being organized in a hybrid mode. The physical event was held on 18th February in London, and the virtual event is being held through Zoom from 19 to 21st February 2025. I hope you will enjoy the knowledgeable and interactive sessions throughout the day. In this session, we have 6 presentations. Each presenter will be given 12 minutes for the presentation and 3 minutes for question and answers. On 10 minutes, I will raise a gentle reminder. There is another request to all the participants that you all stay connected with us till the closing remarks. If you have any query or update, then you can write it to me in the chat box. Now, before we start with the session, I would like to introduce you all to the session chair. We have with us Dr. Ganesh Pisse sir. Dr. Ganesh is an experienced assistant professor with a demonstrated history of working in the professional training and coaching industry. Skilled in jQuery, HTML, software development, JavaScript, and web services, he is a strong education professional with a Master of Engineering focused in computer engineering from SKNCOE Pune. I welcome you, sir, to the session, and I request you to share a few remarks you may have for the presenters here.
Thank you, ma'am, for calling me as a session chair. I will be there for this session. Thank you so much.
Okay, thank you, sir. We will be starting with the presentations now. I would like to call upon Eric Verdugo to present their study on a structured approach to software defect classification and explanation, random forest and gradient boosting ensembles with a focus on prediction interpretability. Eric, sir, are you here with us?
Yes, I'm here. Okay. A minute, please. All right. Good afternoon, everyone. My name is Eric Verdugo, and I'm pleased to present my work title, A Structural Approach to Software Defect Classification and Explanation. The main goal of this study is to improve detection of software defects using advanced machine learning techniques, in particular using like a random forest and gradient boosting. We know that in engineers, software engineer, detecting defects early is critical because it saves time, reduce maintenance, saves time, cost, and this is very important in this part, you can say. Okay, in introduction, we have a cause defects software that's causes estimated 156 trillions in global productivity lost annually. So this project additionally over 30% of software development projects may fail to face or measure states backs due to undetected effects. Okay, one of the major challenges in this balance is that defect data sets, typically about 80%, and free defect free models based 20%. That's defective makes prediction further. So the goal of this is improve defect detections using emblem ML models like random forest, random boosting. plus interplanetary methods like slab, SHAP, or line. Okay, in the research objectives, we have uh, the balancing techniques like smooth balancing, Nermis, Stoke, uh, Stoke Tomelix, and we have these to address to class imbalance problem. When to compare machine learning models, we specifically the random forest, random boosting, SVM of K nervos, or we well know imbalanced datasets. That's JM1 from software and defection and prediction research. We using tools such as lab or line to explain how which models arrives at these predictions to ensure transparency and trust in the result. In this, we have a dataset and preprocessing. We use the dataset JN1, which contains with various software metrics in curious lines of code like log, cancelled metrics, and this information about where each modules in defect are or not. That dataset is highly imbalanced. Approximately 80% of modules are defect-free. So the 20% are defects. So we are processing steps includes, and first we have having missing values. That's we use a most frequent values of each columns to include missing data. Okay, we have a label encoding for any categorical features and we use a label encoder to convert a term into numeric format. Okay, we have this that biology techniques with first smooth try to smooth is oversampling to minority of class. Advanced adaptive oversampling, focusing on harder to learn classes. Links removes noises and borderline samples. And the normies under samples, the majority classes is careful. Okay, in these models and methodology, we have in the 4 phases. The first phase, we have analytics and preparation of data. Late, we got charge and exploration of data, processment, and visualizations of this data. With that balanced data, yes, with advancing learnings, random murder, and smooth plus time links. In the second phase, we use moderate optimizations. I designed a model with random forest, random boosting, K neighbor, and SVM, include with the optimization. In the third phase, we have an evaluation of predictions, interpretation, and comparison of results. And last, with the fourth phase, we have an explanation of predictions. Later, we have analytics and the visualizations of these explanations and predictions. Okay, we have a result overview. Indeed, we have a new findings of like random forest performing exceptionally well, are achieving near perfect and perfect metrics. Precision recall on F1 and it's a 1. It's a 1 to 0. Under K-fold, cross validations, in no doubt it's showing strong performance as well as precision 0.50 75 recall we have is 79, and F1 we have a 1774. So we have a gradient also that's also score is it's 1. That is a good precisions. And recall on F1 we have in the include to validation of every and fit chip split. We have another models that's KNN that's moderate results and very limited to sensitivity to number and neighbors at the distance metrics. And this is a summary about these results. In the interpretability and shapes line, we have a beyond high accuracy interpretability was a key focus. We use a SHAP, that's the meaning of Shapley additive explanations, to qualify how each feature influences individual predictions. In another case, we have a line, that's the meaning of local interpretable model and agnostic explanation, to generate a local explanations for single predictions. Okay. The top features that typical include, we have a local total that's models with here number of lines of code that to more defects prone. Fastest mode reflects the complexity to mode based, more complex detections and harbor more defects. And the last calculate effort, we have a highlight and to level effort needed to understand or modify the code correlating with the potential defects. Okay, in this number of operations, we have this discussion and conclusion. In conclusion, our four-phase approach to data loading and explorations into with prediction explanations provide highly effective and identify software defects under class balances conditions. The ensemble models random forest and random buses that demonstrate the super accuracy across multiple metrics. So it's a robust thanks to balancing techniques like smooth and Adasign, and it's transparent. That's decision making without interpretability methods such as shape or line. That is like important in this whole project. So future work, we can investigate advanced algorithms such as JX Boost, light GBM, yes, which often provides additional gains in speed and accuracy. So we need more exploration about the sophisticated hyperparameters, optimization, grid search, random search, or kinetic algorithms. We expand the dataset with other future engineers, potentially incorporating process metrics like the developers' activity or code review data. So apply these strategies, that's combination about balancing methods to filter enhance predictive and performance. So this is my project. Thank you.
Yes, Mr. Very nice presentation. Can you go to the slide number 5?
Excuse me?
Can you go to the slide number 5? Slide number 5. Slide number 5.
5. Sorry, I can't understand. 5. Yes.
Just move to the slide number 5.
Yes.
This is the 7th. Yeah.
Okay. Sorry. Excuse me.
Here, you have used the data splitting technique, 80% training, 20% testing. Just can you tell me the what is the value for the K? What
Sorry.
is the value of K here you have used during the cross validation?
Yes, we use cross validation to use and have a very good entrainment to this. Yes, for this application and the bear for bear this the detect of these errors and problems we have in the code. If that was your question.
Okay, fine. Go to the slide number 8.
Number 8, okay, 7 and this 8. Okay, results overview.
Can you justify here what is the difference between this random forest k-fold result you have shown? At the same time, you have shown the gradient boost result 80-20. Can you justify it once again? How you are going to compare these things?
Okay, in this image, we can see that a random forest with a call out don't have the better results, but we use a random forest with scaffolds. We have the best motivation to this project in the same case. Another, we have a gradient boosting with this area and 20%. We have the same punctuation. That's good, but we compare it to SBM or KNN. That's very low. So it's not have to use and predictions in this project. Okay.
Okay, fine, fine. Ma'am, over to you.
Okay, thank you, sir. Now, before we move any further, I would take a quick moment to extend a warm welcome to Professor Ahmed Nishad, sir, who have joined us as our session chair. Professor Ahmed is a senior lecturer at the University of Technology and Applied Sciences, IBRI Oman. His expertise spans artificial intelligence, image processing, security, and software engineering. With a strong academic and research background, he focuses on advancing intelligent systems, enhancing security frameworks, and exploring innovative applications in image analysis and software development. I welcome you warmly, sir, and I request you to share any word you may have for our presenters here.
Hello, good evening, everyone. Thank you for a nice introduction. Uh, I expect very useful interactive sessions from the speakers. Hope for the best. Thank you.
Thank you, sir. And please ask any questions you may have for our last presenter, Eric.
Yeah, I have one question. From the data sets what you have used, what are the significant parameters you think that is influencing your results?
Oh, okay. Sorry. Parameters. Sorry, can you repeat again the question?
Yeah, from your data set used, could you tell me what are the significant parameters that is influencing your results?
Okay, the parameters to influences is better to can show you again this
Which parameter you
the
think these are significant parameters
okay the parameters
from your
important
findings? Yeah.
to yes I give me a minute. I don't know. Okay, this the first I can say with the lines of code, the volume to complexity that have a code, and the efforts of time to is to compilate the program. I have the we go to the conclusions that three are the best yes attributes to where to have a good explanation yes prediction of these errors of these problems we can say.
Okay. Have you done any pre-processing of your data set? before conducting the experiments?
Yes, I think these the better lines, the better things that we can use for this preparation of this data set. So it is very good to use local total as a volume, this and the however, it's important to have nav operators or operands. That depends of which is the more quantified of whiles if have in the code. The whiles. Okay.
Okay, thank you.
Okay, thank you, Eric, for your presentation. Now I would like to call upon Salma Mossad Mohammed El Feki. Ma'am, are you present? Salma, ma'am? Okay, I'll be moving on with the next one. Ananya Deshpande, can you hear me?
Yes, ma'am. Can you hear me?
Yes, hello, ma'am. Please present your paper on machine learning driven node compaction for enhanced hardware Trojan detection and runtime monitoring.
Yes, ma'am. Thank you for giving me this opportunity. I'll share my screen once. Are you able to see my screen?
Yes, ma'am, we can see your screen.
Okay. So, hello everyone. I'm Ananya Deshpande. I'm an undergraduate student researcher from PS University, Bangalore. So, I'm excited to present you on our topic, machine learning driven node compaction for enhanced hardware Trojan detection and runtime monitoring. This project has been done in collaboration with our co-authors Akshay Angadi, Amulya HS, Adokshaja, and Nirmala Devi ma'am, who have significantly contributed for our work. We have addressed the effects of hardware Trojan during runtime monitoring phase. So this is the contents for our presentation. Let's begin by discussing about the basic important definitions that we require. First one is hardware Trojan. Hardware Trojan is a malicious modification in the hardware design of an integrated circuit. So hardware Trojan is a small piece of hardware that is hiding inside a large piece of integrated circuit. So here on the right side, if you can see, this is the original circuit and this is the hardware Trojan that has been put into an original Trojan. Basically, hardware Trojan has two components, trigger and payload. Trigger decides when a hardware Trojan has to be activated, while payload decides what happens when a hardware Trojan is activated. So this is the malicious modified circuit where we had our hardware Trojan into the original circuit. Rare nodes. The nodes that have a rare switching activity during circuit operation. These are the nodes at which a particular hardware Trojan can be inserted. Next comes runtime monitoring. It refers to the process of continuously observing and analyzing the performance, behavior, or status of a circuit while it is operational. Next coming to the motivation. The main motivation for our project is the growing threats that has been in the recent years in the modern ICs that is creating a lot of risks in critical applications like aerospace, defense, autonomous systems. So there is an essential need for early identification of these hardware Trojans, which prevents breaches and maintains security standards. So there are three phases for hardware Trojan: design time, test time, and runtime. Unlike design time and test time, which mainly focus on identifying potential vulnerabilities during that particular phase, runtime monitoring provides a comprehensive coverage of the by providing by detecting throughout the lifetime of an integrated circuit. So in our project, we are using runtime monitoring phase. So coming to the methodology, firstly, we take a standard gate level netlist from trust hub circuits. So we have taken around 16 trust hub circuits in our work. So we do the feature extraction part. For feature extraction, we calculate these feature values for all the three features that are mentioned here. That is vulnerability factor, transition probability, and controllability and observability. Vulnerability factor is nothing but how susceptible a particular node is for inserting Trojans. So it is calculated as P0 minus P1, where P0 is probability of being 0, of a signal being 0, and P1 is the probability of a signal being 1. So higher the value of vulnerability factor, higher is the chances of that particular node to insert a Trojan. Second is transition probability. Transition probability specifies as the likelihood of a particular signal to switch between the two states, that is 0 and 1. So it is computed as P0 into P1. Again, P0 and P1 are the probability of a signal being 0 and 1 respectively. So higher the transition probability, higher is the switching capability, and lower the transition probability, then that particular node is stable. So we prefer a transition probability value to be lower as far as possible. Next comes controllability and observability. This is also called scope feature, which abbreviates as Sandia Controllability and Observability Analysis Program. So controllability is how easily a particular signal can be set to a desired value from the primary inputs, while observability refers how easily a particular value can be observed from the primary outputs. So these values are calculated from an open source tool called testability measurement tool that we have used. So these are the three basic features that we have used, and we have found out the values of these features for all the nodes in a particular netlist. Next comes node compaction on dataset. So we have reduced the dataset. So in particular, a particular gate level netlist has around 1,000 nodes. So we have tried to reduce the dataset by using node compaction method, where it reduces the size of the dataset by reducing the redundant feature values and it to a particular single representative. So this is done, and we take the node compacted data set, and then we give it to XGBoost classifier for classifying the Trojan infected nets and Trojan free nets. XGBoost classifier is a strong predictive classifier which has multiple weak learners, that is decision trees. So having multiple algorithms come together gives a better result. So XGBoost model gives us classifies looking at the values of the features. It classifies the nodes as Trojan infected and Trojan free nodes. At the Trojan infected sites, we assign checker logic. We insert a checker logic. So what is a checker logic? Checker logic is monitors the functional integrity of a particular circuit. So it checks the modified signals, modified circuit signals and the original signals. And if there is any deviation between the correlation of the signals, then it throws an error. It shows us that there is an error and there is a Trojan present in that particular circuit. So moving on to the next slide. So this is the design of checker logic. Here, if you can see, this consider this as a particular net, and the target node where the hardware Trojan is inserted is yes. So for this particular circuit, we have A equal to, consider if A and B are 1. If A and B are 1, then the output must Y1 should be 1 and 1 respectively. So if the outputs Y1 and Y2 are not equal to 1, then it throws an error and it says a particular hardware trojan is present. Likewise, if A is equal to 0 or B equal to 0, then X1 and X2, Y1 and inverted X1 must be equal. Similarly, Y2 and inverted X2 must be same. So if this is not present, then it throws an error that this particular circuit has been inserted with hardware trojan. So this is the checker logic for this particular design of the checker logic for this particular logic here. So if you can see this, we have a mux here. So this input signal, the NAND gate having A and B as the input values, is given as a select line. So this select line takes which one to select. Like if this is if this is present, then 0 is selected, and if this is here trojan is present, 1 is selected. This way it provides an error. So coming to the results part, feature calculation. This is our data set. Here we have node names. This is P0 and P1 values, vulnerability factor, transition probability. And since we are using a supervised learning approach, we while training the model, we assign labels for the Trojan nets and for the non-Trojan nets and the Trojan nets. And CC0, CC1, CO are the controllability and observability values.
Excuse me, ma'am.
Yes.
Sorry to interrupt, but this is a gentle reminder that out of the 12 minutes slot of yours, 10 minutes have passed. All right?
Okay. Thank you. So this is node compaction analysis. So here using node compaction, we have a total number of nodes as 1000, ranging from 1000 to 2500. And then after node compaction, it has reduced to which is ranging from 50 to 100, that 900 also, where the reduction percentage ranges from 63.29% to 95.49%. This is the execution time that has been measured with and without node compaction analysis. This is the machine learning model. So we after the node compaction analysis, we could see that true positive and true negative are increased, and false positive and false negative has come a little decreased. So because the number of nets are huge here, this particular column has huge nets, but the false positive and false negative has gradually reduced with node compaction analysis. So this is the diagram of C17 circuit with the 3 NAND gates, and here we have added a Trojan for this particular C17 circuit. So this is the synthesis for the C17 circuit. This is the expanded view of the checker logic. This is where if you can see, I'll just, okay. So the number of Trojans is 1, and type is combinational, and the effect, the Trojan is inserted at N11 node, and it is triggered by N3 and N6 signals. So here, here N11 and N11 is the Trojan infected circuit, and Troj N11 is the original circuit. If you can see here, Troj N11 has 1 and Troj N11 has 0. Hence the error signal is popped up. It shows an error. Similarly here, the N11 circuit is 0 and Troj N11 is 0. So the error signal is 0. So this way, it checks for the error throughout the lifetime of the circuit. Similarly, for C2670 circuit, the same operation goes on. And here, this is the same operation. N297 is the Trojan circuit, and these are the internal signals. So temp and 297 is 0 here, is 1 here, and N297 is 1 here. So that error signal is 0. Here, temp N297 is 0 and N297 is 1, so error signal is 1. This way we have calculated, found out the hardware Trojan for over 16 trust up circuits. So conclusion and future works, node compaction has proven to be promising for improving circuits efficiency, reduce execution time and enhance the accuracy. So, and runtime monitoring through checker has strengthened the method by enabling immediate detection of irregularities, and future improvements could include extending the approach to sequential circuits by incorporating temporal features. So this is all about my presentation. Thank you.
Uh, what is the dataset size you have used?
Sir,
Dataset size.
dataset size is, sir, that's what I told you earlier. We used, before using the node compaction technique, the size was over 1015 to 2500, if you can see here. Total number of nodes is 1015 for one particular circuit. Similarly, for this circuit, it is 2453. So that due to the huge size, the execution time was very high, and the performance also was very low. So we came up with this new technique where we reduce the nodes, redundant feature values, and thereby we could reduce the node compaction, reduce the dataset size. So 251 for this particular circuit and 895 for this particular circuit, and the reduction rate is as follows: 63% and 94.98%.
Okay, fine.
Ahmed sir, do you have any questions for her?
Yeah, one question. Thank you for your
Yes.
presentation. For training this circuit, which algorithm, have you used any machine learning algorithm, anything like that? Means
For
which
train,
algorithm use?
so for training, we used K-fold cross-validation for training, but the algorithm we used for classifying is XGBoost algorithm, sir. XGBoost classifier.
Okay. So do you think that that algorithm was helpful as per your requirement or expectations?
Yes, sir, it was really very helpful. Using the K-fold cross-validation algorithm, the training for training was really helpful. As we have a lot of data set, huge data set, so the algorithm wasn't able to learn properly. But then by using the K-fold cross-validation, we got better results. The accuracy also improved. So as we are using supervised learning algorithm, we had to go through a lot of problems because the data set was very huge. So this way, it actually it helped a lot, sir.
Okay, very good. Thank you.
Thank you, Ananya, for your presentation.
Thank you.
Now, due to technical error earlier, Salma couldn't present. Salma, are you here with us now? Salma, if you can hear me, please reply. No, we still cannot hear you, ma'am. I will be calling your name again after a while if that's all right. No, ma'am, we cannot hear you. I will be moving on with the next presentation. Salma, please wait for your turn. I will call you again if that is all right. Okay? So next up is Kevin Lachpok. Kevin, sir, are you here with us?
Yes, I am here.
Yes, sir. Please present your paper on performance of the fast Fourier transform with neon instructions on an ARM Cortex A72. And I would also request all the presenters to please adhere to the 12-minute time limit of the presentations. All right?
All right, thanks.
Thank you.
Can you hear my, can you see my presentation?
Yes, sir, we can.
Okay. Uh, Good afternoon, everyone. My name is Kevin Lajpop. I am from Guatemala, and I am a PhD student in computer science at the Universidad Francisco Marroquín. Today's presentation is the second part for my doctoral research, which focuses on the fast Fourier transform applied to polynomial multiplication. Specifically, I will discuss an optimization using a neon instruction on Cortex, on IRM Cortex A72. So, the fast Fourier transform is an efficient algorithm that converts the signal from the time domain to the frequency domain. And it is an optimized version of the discrete Fourier transform. However, the discrete Fourier transform has a computational complexity of the big O n squared, making it inefficient when handling a large amount of data. For example, high degree polynomials. This is where the fast Fourier transform provides a significant advantage. The key idea behind the fast Fourier transform is break down the computation into smaller subproblems while reusing intermediate results. The method involves splitting a discrete Fourier transform of the size n into two smaller discrete Fourier transform of the size n over 2, and recursively applying the same process. But by computing multiple smaller transforms, at some point, the results have already been calculated, eliminating the need for redundant computations. And this principle is based on the periodicity of the discrete Fourier transform. So, one of the most important applications of the fast Fourier transform is a polynomial multiplications, which plays a key role in the fields like a post-quantum cryptography or another applications. In this context, the fast Fourier transform can be used to efficiently multiply polynomials by treating them as the discrete signals instead of the performing traditional multiplications, which has a complexity of big O n squared. Fast Fourier transform reduce it to the big O log on n, specifically improving performance. For example, consider two polynomials applying to the fast Fourier transform. We first represent them as vectors paired with zeros to the nearest power of 2. Here, polynomials paired with zeros. We evaluate them roots of the unit performance pointwise multiplications. And finally, we use inverse Fourier transform to the retrieve coefficient of the resultant polynomial. In this case, here, recursivity pointwise multiplication, and here, inverse Fourier transform to retrieve the coefficient, the resultant polynomial. This process makes a fast Fourier transform-based polynomial multiplication significantly faster, especially when dealing with a large polynomials or polynomial with a high degree. What is a neon instruction? Because this research is optimization with the neon instructions. A neon instruction is advanced single instruction multiple data technology in IRM Cortex A72 architecture. It allows a parallel computation, making ideal for optimization mathematical operations. For example, in this case, like a fast Fourier transform. By using neon, we can process multiple elements simultaneously, significantly reducing execution times. Instead of performing operations, significantly neon enables vectoric operations. For example, vector addition or vector multiplication. In this case, this is a vector multiplications. So, for example, the standard fast Fourier transform requires n log n complexity multiplications. But the neon instruction, we can execute 4 multiplication in parallel. And this parallel provides a remarkable performance boost, specifically when applying to polynomial multiplications. So for this experimental, to validate effectiveness of the fast Fourier transform with neon, we conducted experiments on the Raspberry Pi. And the Raspberry Pi 4 equipped with a Cortex A72 processor, 8 gigabyte of RAM, and 64-bit architecture. And the test involved 1,100 evaluations, excuse me, for the each polynomial degree, from the degree 1 of the degree 2000 with 2048, measuring the execution time in nanoseconds. The implementation was tested in 2 configurations. First, the standard fast Fourier transform without neon instruction or without neon optimizations. And the second, the fast Fourier transform using neon instruction or neon optimizations. The execution times were recorded and the performance improvements were analyzed. And the results, clearly demonstrate the impact of the neon instructions. Without neon instruction, polynomial multiplication using a fast Fourier transform took 29 milliseconds for the polynomials of the degree 2048, which is a significant delay in multiplications, in polynomial multiplications. With the neon instructions, execution times decreased by 99.99%, as shown in the following in these comparisons, and the all degree decreased by 99.99% as in execution times. For the degree 1, with degree 2, 2 degree 2048. 48. So this result confirmed that confirmed that neon instructions significantly reduce execution time, making the fast Fourier transform a high efficient choice for the polynomial multiplications. Additionally, when comparing the theoretical complexity of the fast Fourier transform is a big O of n log n, we observe the fast Fourier transform with neon falls below the expected complexity curve. Here the theoretical, and here and the fast Fourier transform with neon instructions. Indicate hardware level optimization further enhance performance. The most fastest fast Fourier transform with neon is 99.99%. And the conclusion and the future works. The fast Fourier transform with neon implementation has demonstrated a significant performance gains, reducing execution times by the 99.99% compared to standard fast Fourier transform. The future work could explore testing on the different ARM processor, for example, Cortex M4, and for example, evaluate energy efficient, comparing another technology, for example, GPU optimizations, and the apply to this optimization into real crypto systems, for example. In general conclusion, this research highlights that hardware optimization play a crucial role in accelerating cryptographic computations. By leveraging neon instruction, we have demonstrated that the fast Fourier transform based polynomial multiplication can be significantly improved, making it a viable solution for the real world and other in diverse applications. And thank you for your attention and your time and this time for the questions.
Ganesh sir, do you have any questions for him?
No, ma'am. No question from my side.
Okay. Ahmed sir, any questions for Kevin?
Thank you, Kevin, for your presentation. So when you try to introduce new instructions, what are the new challenges you have faced comparing to the previous one without new instructions?
A challenge is compared with another optimization. For example, a barrel shifter operations. The barrel shifter operation is instruction in another family of the cortex. In this case, cortex M, M4, M5. And the first challenge is comparing with in twice optimizations and evaluate one is more faster in different scenario.
Okay, thank you for your presentation. Thank you.
Thank you.
Thank you, Kevin.
Madam, can you hear me now?
Yes, Salma, we can hear you now.
Can I present now?
Yes, Salma, please start with your presentation.
Thank you. Now you can see my presentation?
Yes, ma'am, we can see your screen.
Okay, good evening, everyone. My name is Salma, and I am going to present our research automated MLOps driven YOLO framework for drone-based plant detection. Author Salma Musad Al-Fiqi, Minnatullah Nafadi, and Ali Hamdi. This work has been carried out at MSA University, Egypt. Introduction. First, we will start with AI in agriculture, machine learning, deep learning, automated plant detection, improved food security, and crop yield optimization. Limitation of traditional method, manual field inspection, slow, error-prone, not scalable. Drone deep learning integration, drone capture high-resolution image for real-time monitoring, challenges, lightning, weather, crop cross variation. Proposed MLOps pipeline, automate YOLO model V5, V8, V9, and V10, training and deployment. Use continuous integration and continuous delivery for continuous improvement scalability. Our motivation is precision in agriculture need. Traditional plant seed detection rely on manual inspection, which is time-consuming, prone to human error, and not scalable for large farm. Drone technology potential. Drone equipped with high-resolution camera can capture detailed imagery for early disease detection and intervention. Challenge and model deployment. Existing plant seed detection system lack automation, scalability, and adaptability to changing environmental conditions. MLOps for efficiency automates the entire machine learning pipeline, training, testing, and deployment, ensure real-time performance optimization, reduce dataset imbalance, and improves accuracy. Enhancing food security, efficient plant seed detection contribute to global food security by minimizing crop losses and optimizing agricultural yield. The dataset that we use to train our model is cashew disease identification with AI details, 4,736 high-resolution image, about 1,600 by 1,300 pixel each, annotated in YOLO format for efficient object detection. We have three classes in our dataset: insect, abiotic, disease. Class imbalance challenge due to an instance of insect 1,618 and an instance of abiotic 30,960. An instance of disease is 732. Our objective is to develop an automated drone pest disease detection system. Use YOLO models, YOLO V5, YOLO V8, YOLO V9, and YOLO V10 to detect plant disease from drone imagery. Implement an MLOps pipeline for continuous optimization, automating training, testing, deployment process for real-time UAV integration. Ensure robust model for performance across different conditions. Address dataset imbalance using increment dataset expansion and data augmentation technique. Compare YOLO model performance, evaluate and benchmark different YOLO versions to determine the best performing model for specific disease categories. And in the final, we enable scalable and adaptive disease detection, ensure the system that can continuously improve by integrating new data and adapting the environment variation. Our problem statement is traditional plant disease detection rely on manual field inspection, which are time-consuming, error-prone, and unsuitable for large-scale agricultural operation. While drone equipped for high-resolution camera offer an promising solution for real-time monitoring and apply deep learning model in agricultural environment present. Challenges such as variability in lighting, weather condition, and the crop growth stage. Additionally, existing computer vision-based systems often lack scalability and automation, limiting their effectiveness in dynamic farming conditions. Our methodology is first, data collection and pre-processing. High-resolution image 1600 by 1300 captured via P4 multispectral drones. Data augmentation like cropping, flipping to handle dataset variability. Labeling, structuring, categorization into training, validation, and the test sets. Iterative training, continuous integration, model selection, YOLO architecture initialized with optimal hyperparameter, increment scaling, training start with small dataset and progressively expand, real-time monitoring, track matrix, mean average precision, and recall to optimize performance. Evaluation and continuous delivery model is validated on test dataset before deployment. Deployment real-time monitoring, UAV integration, model deployment for real-time inference for drone system, feedback loop, continuous monitoring for accuracy and predictory training. Our model design, first data collection and pre-processing. Dataset that we talk about, KDAI dataset, 4,736 high-resolution drones image for cache crop. Image resolution about 1,600 by 1,300 pixels. Our class is abiotic, insect, and disease. Pre-processing, data augmentation like flipping, scaling, rotation, image annotation, and data structuring for training, validation, and testing. MLOps pipeline for automating model and deployment, continuous integration, and then continuous deployment. Continuous integration include iterative training using increasing dataset size from 757 to 3,788 images. Euro architecture train with real-time monitoring of performing metrics, hyperparameter tuning, learning rate, batch size adjustment. Continuous deployment, real-time inference, and model integration with UAV system. Automated update based on model performance evaluation and feedback loop for retraining with new data. 3. Model training selection. YOLO version used, we used YOLO version 5, YOLO version 8, 9, and 10. Training process, model trained on progressively large dataset for better generalization. Adam optimizer with learning rate scheduler. Evaluation matrix, mean average precision, and recall, class-wise performance, insect, abiotic, disease. Deployment and real-time monitoring. Integration with UAV system for real-time disease detection, continuous monitoring for deploy model to ensure performance consistency, feedbacks based model retraining to enhance detection accuracy. This is our model architecture. The process starts with a drone with capture image of crops. Then this image goes through a processing stage where we perform data augmentation, labeling to enhance the dataset. Then the dataset is continuously monitoring and fed in continuous integration, continuous delivery, which includes 3 phases. First, training, then evaluation, then deployment. After deployment, the train detection model is used in drone plant disease identification. This is our result. for UV5, UV5, 8, 9, 10. We have 5 iterations for each one of them. In the first iteration, we used 20% of the dataset. In the second iteration, we used about 40% of the dataset. In the third iteration, we used about 60% of the dataset, and in fourth operation, we used about 80% of dataset, and in the last iteration, we used the full version of dataset. Conclusion: this study evaluates the performance of UV5, 8, 9, and UV10 for plant disease detection using drone imagery enhanced by MLOps pipeline for iterative training and deployment. UV5 shows the best overall detection accuracy, while UV9 excelled in identifying abiotic threats. The progressive improvement in UV5 and UV8 highlights the effectiveness of dataset augmentation and automated optimization. The challenge remains due to environmental variability and the suitable nature of disease symbolism. Further work should focus on diversifying dataset and integrating multispectral and hyperspectral imaging to improve detection accuracy. This will further enhance real-time drone-based monitoring, advancing precision agriculture through time intervention and improve crop health. And this is our reference list, and thank you.
Okay, a very nice presentation. It is belongs to the agricultural. Can you tell me just whatever the data set you have used, whether you have taken it is from the authorized organization or you have prepared your own data set?
No, we use our dataset from Kaggle,
Okay.
and the image
Okay, for image processing, which algorithm you have used here?
we use flipping, rotation, and we use also class balancing.
Okay, fine.
Ahmed sir, do you have any questions for her?
Yes, regarding data set, my question is whether all the images in your data set are of same data type and are all of same size, or it is different data types and different sizes.
Yes,
How was your
sir.
data set?
Yes, sir. Our dataset was in the same type, and in the same size.
Okay, so the images captured from drones are of same data type and same size.
Yes.
Do you expect the same thing? If the
Please, can
drones,
you repeat, please?
yeah, the images captured by using drones are
Yes.
is also of same data type and of same resolution type, everything is the same like one you have in your data set.
Yes, sir.
Sure.
Yes.
Sometimes if the drones are of different kinds, then the image captured may also vary, right?
Yes, you're right.
Yeah, so in that case you have to do some pre-processing, right,
Oh,
to
yes.
make it a standard size. Otherwise your results also may be affected. Okay.
Yes, sir. But we also make a pre-processing.
Yeah, actually the drones which you have used, whether that image is also of same kind or different, that was my question.
Okay, sir.
It's same? It's the same?
Can you repeat, sir, please?
The drones which you used, which captured the images and your dataset images, both are one and the same, or it's different?
Actually, we didn't use the drones. The image in the set was already in Kaggle, so we used only the image.
Use only the dataset image. Okay.
Yes, we take it from Kaggle, and it was in Kaggle, so we used.
Okay. Thank you.
Thank you, sir.
Okay, thank you, ma'am, for your presentation.
Thank you.
Now, next, I would like to call David Alvarado. David, sir, are you present?
Yes, I'm here.
Yes, sir. Please present your study on PET image classification for lung cancer diagnosis deep learning with transfer learning, data augmentation, and region-based prediction explanation by integrated gradients. Sir, your audio is off, sir. Excuse me. Yes, sir.
Yeah. Hello, everyone. My name is David Alvarado, and I'm from Cuenca, Ecuador. And I'm going to talk about PET image classification for lung cancer diagnosis, deep learning with transfer learning, data augmentation, and region-based prediction explanation by integrated gradients. I am a student of the University Politécnica Salesiana, and my partners are Diego Loja and Remigio Hurtado. Well, the content is the next is as follow: introduction, related work, purpose, method, design of experiments, results and discussions, conclusions and reference. Well, let's start with introduction. The lung cancer is one of the most deadly sick in the world. In the year of 2020, it was estimated to cause approximately 2,200,000 cases worldwide and resulted in 1,070,000 deaths. This data showed that this causes more deaths compared to other types of cancer. Distinguish between types of cancer is a challenge for physicians. Well, we can have two types of cancer. That is the non-small cell lung cancer and the small cell lung cancer. In the case of the non-small cell cancer, we have three subtypes, que es adenocarcinoma, squamous cell cancer, and large cell cancer. What is the objective about this work? The objective is to support image recognition and processing using machine learning methods. Well, first we give us an information about the dataset. The name of the dataset is Lung PET CT-DX. This is a large-scale CT and PET CT dataset for lung cancer diagnosis. In this case, the dataset, it doesn't have a study variable, but based on information from the dataset, with classification of type of cancer can be determined with patient code. In the categories, we can find the letter A means adenocarcinoma, the letter B is small cell carcinoma, the letter D is large cell carcinoma, and the letter G is squamous cell carcinoma. One characteristic, principal characteristic of this dataset, we can see in this frequential diagram. The things we can see is that this is an unbalanced dataset. This can make we can find here the adenocarcinoma that is more than large cell carcinoma, small cell carcinoma, and squamous cell carcinoma. This gives us a problem because in the moment of make the prediction can give us error. Well, the related work, we can see pre-related work. The PET image from the long PET CTX dataset are processed and used to train CNN, BGG is 16, and ResNet 15. These two are convolutional neural networks, and with an RNN, the CNN achieves the best performance with 5 accuracy and 6.3 precision. The sensitivity of this work is 0.83 and the specificity is 0.63. Other related work is a study on lung cancer classification and prediction using machine learning and image processing found an artificial neural network of performing models like CAN-NN and RF, achieving over 90% accuracy, specificity, and sensitivity. Additionally, a comparison of RF, SVM, and ANAN for lung cancer prediction with CT image showed that ANAN achieved 92% accuracy for regional predictions and 96% for texture basis and prediction. Well, we can see here the proposed method. We we made the proposed model is made for data loading, for PET scan escalation, RGB conversion, image sequence, and data preparation. That's the phase one, that is the image preparation. Also, we have the phase two, that is for experiments. We have the models building, the training and testing, and the result. And the phase three is for prediction, the models and prediction. Something interesting about that is the data preparation. The data preparation, we have five phases. The data loading, the first step is to load the dataset long PET CTDX, which contains all the necessary information about that. The PET scan selection, something about that dataset is have not only have image about PET, also have CT image that we don't use because it was a huge dataset. Well, in this case, in the PET scan selection, only PET images are extracted and also contain CT image. The after is the RGB conversion. The images are converted from DCOM, that is a format that use the image PET, and this convert to RGB format, separating in the three canals, that is red, green, and blue, which is essential for the subsequent step, that is the video creation. In this, images are converted to videos to facilitate future data extraction for model training. And the last is the data preparation. In this case, in the data preparation that we made is with the video creation, we extracted 50 frames for video, and followed by data segmentation to enhance diversity and robustness. Images are normalized to address environments, categorized, and split it into 70 for training and 30 for test. When we center in the phase two, we use 4 models: Inception Net V3, Efficient Net V0, Efficient Net V2S, and also an SVM. In this case, are convolutional networks, and after this, we use recurrent neural networks. In this case, we can see the design of the experiment dataset. We have 120 PET images from more than 200,000 DCOMS files were used, divided into 3 classes. 95 are adenocarcinoma, 9 small cell carcinoma, and 29 squamous cell carcinoma. Something that we can see in this image is the phase of the data augmentation. We can see in the phase one. We can see something about that is one of the subcategories was deleted because this gives a lot of error in the prediction. The quality measure that we use was the accuracy, the precision, and the accuracy, the prediction, the recall, and the F1. Well, we can see in results and discussion. For example, in Deception Net, we have accuracy of 0.72. Efficient Net was the best of these models, give you a 0.78. We compare with other related works that have a 0.73 and SVM 0.48. We can see here a confusion matrix that give us an idea about the accuracy that we find in efficient net V2S. Where something other step in the phase 3 is the explanation by integral gradients. The integral gradients serve to indicate which areas of the image are decisive for the prediction. Obviously, this only serves as an ID to the doctor. For example, we can see this is a case of a small cell carcinoma, and this is for a case of squamous cell carcinoma. We can find these ingredient gradients that indicate which areas of the image are decisive with color yellow and red and orange.
David, I'm sorry to interrupt, but you have 2 more minutes for the presentation. Is that all right?
So right. Well, and then we have conclusions, that is the efficient net V2S model of the performance order achieving give us a 0.82 precision and 0.78 recall and 0.5 F1 score. It should be noted that more dataset is needed on class B and G, which are small cell carcinoma and squamous cell carcinoma, respectively, signs that are greatly affect training. The implementation of advanced techniques such as data augmentation and integrated gradients has improved both the balance of the dataset and the interpretability of the model. The use of the integrated gradients made it possible to identify the most relevant regions in the image, providing a crucial level of the confidence for medical specialists. It is proposed to explore the integration of multimodal data, CT and PET, and validate the model on large balanced dataset. Well, thanks for your time.
Ganesh sir, do you have any questions for him? Ahmed sir, do you have any questions for David?
Yeah. Thank you for your presentation. Have you tried with any real-time data images?
Not in this case, we try to use the CT, but the dataset about this dataset is very huge. Is approximately is 100 gigabytes, but only with the PET is less than 5 gigabytes.
Okay. So the same model, have you tried with any X-ray images?
Sorry, can you repeat?
Have you tried any X-ray images with the same model for testing purpose? Only CT images, scan images you tried, or X-ray images? You know, it will be black and white, grayscale
Uh,
images. Have you tried that option with your model?
we only use the image PET. In this case, don't use the CT. In this case, we use the conversion in RGB, and we use, in this case, the image PET is only on black and white. But in the moment of doing the prediction, we use a lot of other cases, and we can find in the 3 cases a prediction correct.
Okay, fine. Thank you.
Okay, thank you. Now, next up, I would like to call Eben Francis. Eben, are you here? Eben, I repeat, are you here? Or are there any of the co-authors present? Okay, we'll move to the conclusion ceremony then. I sincerely thank our authors for their excellent presentation and contribution in this session, and all our participants for being a part of this international conference. I hope this session was informative enough. We, on behalf of the whole team, thank you for the support during this 10th version and all the previous 9th versions of the conference. We will be happy to have you in the 11th version in 2026. All the presenters would be getting their digital certificates through email within 2 working days. Further, all the papers have already forwarded to the printer. The publication will be live within 6 months. Kindly cooperate with the team of ICICT 2025. I would like to thank our session chair, Professor Ahmad Nishad sir, for chairing the session, extending a token of appreciation on behalf of Team ICICT 2025 and Global Knowledge Research Foundation and partners. Sir, I will request you to share any closing remark you may have for the everyone here.
Sure. It has been an absolute honor to facilitate these research discussions among some distinguished speakers, and also engaged audience. I sincerely appreciate our presenters for their valuable insights and contributions, as well as to the organizing committee for their meticulous planning and seamless execution of this event. And also, I appreciate you for moderating. Thank you so much for the opportunity.
Thank you, sir.
Welcome.
I would also like to thank Professor Ganesh Pise, sir, for chairing the session. I'm sharing a token of gratitude on behalf of our team. Please share any closing remark you may have for the presenters here, sir.
Yes, ma'am. First of all, I'm thank you ICICT to 2025 for calling us. All presentations was very good. So once again, I thank you to you and your team. Thank you so much.
Thank you, sir. Now, before we conclude the session, I would request everyone to switch on their cameras for a quick snapshot of the virtual conference. All right. Thank you, everyone. Have a great day ahead and take care.
Thank you.
Thank you.
Thank you.
Thank you.